vortex reconnection is the topic, and we're delighted to have Steve in this class.
That can only go downhill after this. Anyway, it's not exactly clear whether vortex reconnection plays a very important role in turbulence or not. Professor Fazleh Hussain thinks it is very important. I think it could be, but I'm not sure. So we'll discuss this as we go along. So what is the vortex reconnection? Suppose you have two vortices like this, opposite sides, and by chance they come close together somewhere along at, let's say, some time, and then they are drawn to each other. They come this way, then they cut, and then they reconnect in this fashion. One half of one vortex, the other half of the other, they sort of join together, and they move off from each other in a different plane from which they were traveling earlier. So this is the vortex reconnection. I think it's sort of a fascinating subject in itself, just by the very rough description I've given, and I've of course given you a very loose description. I will try to improve upon this as we go along. Now, you probably have seen this picture in Mr. Reinreich's album, where you have here an aircraft that has gone off and has left two trailing vortices. And the trailing vortices, as you know, they are oppositely oriented. They actually have circulations like that. And the subsequent pictures are the pictures of the same thing taken at different instants of time. So there is a certain, let's say, instability that brings them close together here, for instance, and then they rejoin in a form that changes the topology and exactly how vortex rings. Although Professor Naguib taught us a long time ago that if you have a tracer, you should not really interpret it completely as a vortices. Nevertheless, I think this illustrates the issue of vortex reconnection. Now, this is obviously a subject of interest, at least to us, and this picture had to do with the growing instability, and this is the first paper that talked about such possibilities. And then there are a number of them here. This is not exactly an exhaustive list, but I think by and large you have many of the important papers. There were many Japanese contributions, as you can see, and of course you also see a familiar figure here, and I stopped more or less in 1995. Now the same crowd of people, or some of the same crowd of people, got interested in Euler singularities around 1995, and that became a fashionable subject, and thereafter stopped working on reconnection. But occasionally you still find papers written on reconnection. For example, this paper appeared in 2007. So it's still of some current interest, but by and large it is a subject which had its maximum interest in fluid dynamics some time ago. Now, the brief description I gave you earlier of reconnection ignores many things. At least two of them are the viscous effect. So clearly, when I was talking about reconnection, the change of topology would not be possible if viscous effect somehow did not come into play. And I didn't mention anything of that. And furthermore, these vortices, at least the ones you saw on the tailing edge of the aircraft, for instance, have a significant core, and that is a very important topic, how in fact the finite core plays a role, and this is part of the work that Professor Hussain has done at some length on. Now, but I will talk about vortices in superfluid medium 2, where there is no viscosity. Superfluidity means, in fact, no viscosity. And the vortices are of the order of a few angstroms, so they are really very tiny in diameter. And then there are, although some quantum mechanical effects will come into play when the vortices interconnect, the usual type of core dynamics that one discusses is not really that significant. So that's the part I will discuss, and perhaps there are some things you can learn about classical resonance as well through this. And in fact, here is a list of references. This is now becoming fashionable in superfluidity. Although it started in 1998, a little bit of that from Paul Schwarz. In fact, most of the papers you see now have come lately, and I started 2008 with a number of other papers in the last year or so. So just to give you a brief illustration of what helium 2 is on this diagram, I plotted a phase diagram of helium here, temperature on this axis, as you can see a few Kelvin. So we are discussing very cold fluid, and here is pressure, and here is the coexistence line, below which you have the vapor state, and above which you have the liquid state. The liquid state has two phases. Helium-1 is a classical fluid which satisfies Navier-Stokes equations, and here is helium-2, which has certain special properties. It is special, you can already tell, because even at 0 K, it does not freeze into a solid as every classical fluid would. So this is some quantum mechanical in nature. And then one of the special properties of that is the superfluidity. And superfluidity is the property of the flow that makes it possible for it to flow without friction, like a fluid. And it turns out when it moves beyond a certain speed, it will spontaneously generate vortices which are very thin, and these are more like the ideal line vortices that you find in classical fluid dynamics. So it is here that it is this part that I will be discussing today. And perhaps I should use a little bit of time to explain a phenomenological model of helium-2. Let me maybe do this as well. If you remember this phase diagram, so this is called the lambda line. So below the lambda line is where superfluidity exists. And what I am plotting here is the temperature below the lambda line, or the lambda point here. So the fraction of the superfluid really is 0 right at the lambda point, but it increases as you go down in temperature. And the fraction of the normal fluid, that is the fluid that obeys the classical equations of motion, is 100% here at the lambda line, and it goes down here. So if you are at any temperature like here, for instance, there's a certain fraction of the normal fluid and a certain fraction of the superfluid. And in fact, these two fluids are supposed to be, according to Landau, who basically promoted this idea, they are coexisting but non-interacting and interpenetrating fluids. So in some sense, Landau knew very well that by making such division into superfluid and normal fluid, he knew that it was not really to be taken literally. He said, we particularly emphasize that there is no division of the real particles of the liquid into superfluid and normal ones, which is no more than a manner of expression. But anyhow, this is the phenomenological model that works, and that's the one we use, and these are the people who really promoted the idea. London and Pizza on the one hand, and Landau on the other, and as you remember, Landau does in the third aspect. So now, the superfluid moves without any friction, and the only way it can more or less do it is if it moves in one bulk. It is not really having any shear attached to it. Suppose superfluid is moving at some speed, and you find a velocity perturbation imposed on it. Now what can it do? The whole flow can slow down in principle, and then it can sort of accelerate again, or it can slow down locally by creating vortices. Energetically, it is favorable to create line vortices, and that is the main recognition that Ansager had. And what Ansager thought was that spontaneously these line vortices are formed, mostly as the favored state in energetics. And these line vortices have a circulation around them, and the circulation is such that the velocity goes down like 1 over r. This circulation that is describing the strength of these vortices is quantized. That is, it does not have any arbitrary value, but it has a value that depends on the Planck's constant divided by the mass of the helium atom. So you have to think of these light vortices with fixed circulation around them, not arbitrary circulation, and somehow interacting with each other. And in fact, this whole thing that Ansar said was this. He basically had this wave function, and here is the phase of the wave function, and the velocity is the gradient of the phase. And simply by requiring that it be single valued, when you go around in one circuit, he said that it has to have a quantum of circulation. And this is the famous statement he made, that the well-known invariant for hydrodynamic circulation is quantized, and the quantum of circulation, as I said, is Planck's constant divided by the mass of the helium atom. So now, this was hypothesized to exist for many years, and people had in fact made calculations on this, but they were not seen for a very long time, and it was only very recently that we were able to visualize them, and it appeared in this paper. So what I'm showing here is a bunch of particles that are distributed in the flow, and what these particles are I will say in a minute. And this would be a little bit above the lambda temperature, and these are homogeneously distributed, as you can see, as you would in fact have if the flow were homogeneously turbulent, more or less. But if you go a little bit below the lambda temperature, you can see these lines that are formed, these lines that are of different shapes formed in the fluid, and these, we think, are the quantized vortices. And in fact, it is not simply this that makes us think that they are quantized vortices, because they sort of appear and disappear if you go above and below the lambda temperature. But if you take the apparatus in which these vortices are formed and spin them around an axis, a vertical axis as in this case, then all the vortices have to align themselves in the vertical direction, because they have to absorb the angular momentum that is introduced into it by the rotation of the global rotation of the apparatus. As in fact you can see, a lot of them are lined up here with of course some defects here and there, but by and large they are all aligned marked by these particles. And what is more, the number of these vortex lines will have to increase as you spin up the apparatus more and more, because the angular momentum will have to be balanced, and in fact the relationship is linear. And Feynman actually worked out what the relationship must be. The number of vortex lines is a function of the rotation of the apparatus, and this was his line. And this is a slightly modified version of his line, allowing for orientation effects. And what you should find, if these were quantized vortices, is that the number of vortices as you measure them or count them ought to lie between these two lines, and in fact that's what by and large they do. So I think these are the kinds of indications that tell you that these are quantized vortices. So now the only reason it was possible for us to mark these vortices, which others were unable to do for a long time, is simply that my students, Greg Bewley and Matt Colletti, working with Dan Letro, were able to devise the right sort of particles. The right sort of particles, I have given here the requirements for particles to be used in a classical fluid, and you can see a lot of that written out in Maxey and Riley. But in liquid helium, there are some special aspects that make it even more difficult, and the particles that I've worked are nearly neutral particles of frozen mixtures of helium and hydrogen. So somehow you mix them in right proportion, and you cool them, and then you can make tiny particles that are neutrally going, and also scatter enough light that makes it possible to see this. So the apparatus is very simple. It's a desktop thing, as you can see, an optical table. So a cryostat, and inside it is the helium, and there are particles introduced, and the particles are marked by the camera usual stuff, like you do with the PIV, for instance, by and large. So the real important thing is the notion advanced by Feynman, 2 points. in this beautiful article. The first thing was that he said, even though these vortices have quantum mechanical origin, if you go away from the vortices, only a few diameters from them, the dynamics is essentially classical. So he said, except for a few angstroms, from the center of the core, the laws obeyed are those of classical hydrodynamics, for example, by yourself. And then he said another one very important thing. He said if two oppositely directed sections of vortex lines approach closely, the lines which are under tension, which is to say they have certain energy associated with them, may snap together and join connections in a new way. He did not use the word reconnection, but that's what he was saying. So I have this is a picture taken from his own paper. So these two vortex lines appearing like this, and a little bit later they might have reorientation like that. So that was the point he was making. So it turns out that you can use these things, the idea of reconnection, and go quite far in certain aspects of turbulence, which I will describe. But now maybe I want to show you, if it works, a little movie on the reconnection of these vortex lines. And I would like you to focus maybe on this part of the picture, where you will see, first of all, you will see lots of particles, and these particles are supposed to be marking the vortices. And at one place you will see the vortices reconnecting and recoiling from each other relatively fast compared to the background. So that is what you should be able to see if this works. So here you see this, how they recoil very fast, and this will replay itself a few times, and you can see them marking lines sometimes. So that is the general idea. So the general idea is you can study reconnections in this fashion. I will stop that. And you can study many properties of these reconnecting vortices in this way. One of the things you can do is to measure the distance between two vortices as they approach each other and also repel from each other. So one before reconnection and one after reconnection. So let's say delta t is the separation distance at any given time t, and by dimensional arguments, it can only go as the circulation around the vortices, which is a fixed number, that has a dimensional circulation, times t to the power half. Half is the only possible number that is allowed by dimensional argument, with this number being arbitrary. So that's what the dimensional arguments will tell. I just basically put alpha here to sort of generalize it, as you will see, for whatever reason. And when you measure these separation distances as a function of time and plot them on a log-log scale, delta here and t here, with some virtual odds in t naught accounting for just the time at which the reconnection starts, you will see that they do in fact follow power laws, but the exponent is not half, but are spread around half. In fact, here is the histogram of these exponents, alpha on this axis and probability of alpha on this axis, with the most probable value around half, but then it has a number of other values as well. Whether these values are really somehow telling us something more different from just the dimensional analysis will tell us, or whether you can somehow redo this in a certain fashion to account for half is another matter. But here is a possibility, for instance. You can always say that you have a first order term which is going like 3 to the power half with a correction for finite time, for instance. You can do it like that for that matter. And then you can find out the right constants A and C and ask yourself whether you get the half power or not. And in fact, it is possible to fit them by this thing as well, all following the half power. So I don't know which is more fundamental in this, but you can always ask yourself what you observe, and what you can always say that what you observe is really for finite time and not really for large times. And when you have finite time, you have other things coming into the picture, for instance, just the dynamics.
Okay. So, possible to ask a question? Fast question?
Yeah.
But can it not be that you don't get the one out just because you have the external two that is all the vortices that
yeah, it is entirely possible. Yeah. Okay. I mean, I will maybe make some remarks on that also. Now that's where we wrote this business up. But the important point is that when you approach the vortices and when the vortices repel from each other, you would think that the statistics of the separation distance would be sort of different because these vortices are supposed to intersect in a time irreversible manner, that is the dissipative events. Now what actually you find is that one of the curves here, red and black, correspond to vortices approaching each other and the other vortices repelling from each other, and it seems like they are indistinguishable from each other, which allowed us to make this remark that maybe the reconnection statistics are time reversible in fact, and this has some important consequences if it were true. I don't know if this is true, only because we are after all observing the vortex lines when they have repelled from each other only after a certain time, because our resolution of measurement is not close enough to get to the real reconnection event, but only after a certain point in time. And of course, all the irreversibility might be happening when they are really very close to each other. So it might very well be that I am not right about it. But one other interesting thing is that, and this is where some possible connection with classical dynamics could be made. If you measure the probability density of the velocity fluctuations, you have, let's say you create many vortex lines, and many of them have interacted and reconnected and all this, and produce a very complex velocity field, and you measure the probability density of the velocity, and what you find is that, ignoring the fact that they are white and red, but red and black, but just concentrate on one of them, let's say on the black, you see that the probability density has tails stretched out like this to very large standard deviations. And except near the wall, in classical fluid dynamics, the velocity distribution is roughly Gaussian. If you take homogeneous turbulence, for instance, it is Gaussian. Now, here, too, there is probably a Gaussian part in the middle somewhere, but the rest of it is stretched out like this. Now, suppose I say, from the conservation of probability here, that the separation distance goes like t to the power half, the velocity goes like t to the power minus half, and this relation tells you that the probability density of the velocity will go like v to the power minus 3, and this is the minus 3 minus third power, this line that is drawn here. So in fact, the tails of the distribution somehow are governed by the reconnection events, presumably, because of the connection I just made. And there is a core there that is probably not related to reconnection. Now this always bothered me in a certain sense, because as I said, if you measure the velocity distribution in a homogeneous turbulence, for instance, you have a Gaussian distribution. And if the tails of the distribution here are connected to reconnection, is it possible that the fact that you don't have stretched tails in classical turbulence means that the reconnection is not important there? I don't know if that is the good and the right logic or not, but we try to measure the probability density of the velocity associated with strong vortex elements, for instance, and this is a conditional measurement, and you can do it for more and more intense vortices in classical turbulence. And nowhere did I see anything like a stretched distribution. And this is from the simulations of Downs and Young. And these are conditional velocities, conditional on the intensity of vorticities, and you always find them Gaussian more or less. So I'm not sure whether it implies that the reconnection, at least as it appears in this direct fashion, is of great consequence or not in classical turbulence.
Excuse me.
why do you study the linear of the velocity and not the vorticity?
You can do for the vorticity too, but I am only talking about velocity. Because velocity, vorticity is stretch distribution anyhow. It has stretch distribution anyhow.
Yeah,
In both cases it is stretch distribution.
Yeah, but my point would be that maybe in classical homogeneous problems, the vorticity distribution would be more relevant for this case of reconnection.
I want to look at the probability density, the same object in both cases, and I want to show, at least in that instance, they are very different in one case compared to the other. If you look at the vorticity, they are stretched tails, but only the stretching is different in both cases, and you would not be convinced so much that there is a big difference, qualitative difference. That was the main thing. So now, this picture is supposed to tell us, this movie is supposed to tell us how the reconnection events leads to very complex motion. So what you see here are many vortex lines, and they are perturbed by the initial condition. And now they are let go, and they are following simply Biot-Savart law. And what you see is in a little bit of time, they become very entangled shape like this, and if you freeze them at any given point, then let's say you place your probe there, for instance, to measure the velocity as a function of time, it will look a very complex object, just as it would look in classical turbulence. And so this is the reason it's called superfluid turbulence. And for the rest of the time I have, I will say a little bit about the possible connection between classical turbulence and superfluid turbulence. So the experiment that will be done now is the following. This is the classical one. This is a picture I took from Park and Nagib, except that they had it from left to right. I reoriented it to illustrate what I'm trying to say. So here is, let's say, water in a tank, and you pull a grid through it, and it produces turbulence, and it is homogeneous and roughly isotropic, and not unrelated to the sort of grid turbulence that one sees in this picture. Now, suppose instead of water, I put helium-2 there and do the experiment, then what will you have? Helium-2, remember, has classical part and the superfluid part. And the classical part will produce turbulence of its own, like grid turbulence, and it will decay like classical grid turbulence will do. And the quantized turbulence will produce, presumably, the superfluid will produce, presumably, quantized turbulence vortex lines, and somehow they too start interacting, reconnect, and so on and so forth, and form this very complex turbulent-like motion. And that too will have to decay because the energy that you put in there is put in only at the initial instant of time when the grid is full. Now in classical turbulence, the decay law for classical turbulence is something that one does not know how to evaluate very precisely. There are no theories. There are all kinds of theories, but there is no real theory. But there is one instance for which you can write down the decay law exactly. And that is possible in the case when the thing is decaying, the length scale grows, and if you have a finite box, for instance, the length scale grows up to the edge of the box, let us say, and it cannot go any further. So the length scale is fixed, then the decay law can be written down precisely. And that's very simple. Here is the equation, energy decay, giving you energy dissipation. And the energy dissipation follows this classical thing. This is 3/2 power of the velocity divided by length scale. This length scale and the velocity are both unknown, and that's the reason you cannot solve it in general. But here, if the length scale is fixed, then it is very easy to solve this, and it gives you the relation epsilon going like t to the power -3, and it also tells you that the vorticity will go like t to the power -3 also, or mean square vorticity going like t to the power -3/2. So now, in the experiments that I am going to describe, which were done this part in Rustom's lab, so I have this tube which contains helium-2, and a grid just like that is put through and here is the mixture of classical turbulence and superfluid turbulence. And what you do is you you send a second sound that is just a heat pulse, and the heat pulse, as it propagates through this, will be absorbed by these quantized vortices, and the attenuation of the pulse you measure on the other side will tell you something about the intensity of the vorticity. And what you find is the following: as a function of time, as a measure of vorticity here. So this is the -3 horsepower that is applicable to the classical turbulence when you have the length scale not growing any further. And what you find here for the quantized turbulence is something very similar, also following the -3 horsepower. And you can do this for different Reynolds numbers, actually means different temperatures, which means different viscosities. And you can collapse all of them, not only in this power law, but by and large everywhere except for these long times. And the way you can collapse them is simply collapse them on the basis of what you think should be done in classical turbulence. For example, there is a certain drag on these objects, these rods, and you basically, Bachelor showed us in a footnote how to do this. So the general idea then is that you have the decay law of superfluid turbulence obeying the same law that classical turbulence does, and also the prefactors in front of the decay law also is similar to what is found in classical turbulence. So one more thing, and then I will wrap up. From these decay laws, you can actually measure the effective viscosity associated with the decay of this tangle of quantized vortices. And this is very similar to the effective viscosity of classical turbulence, except that we know the effective viscosity of classical turbulence will depend upon the geometry, will depend upon a number of other things. But here it turns out, if you measure the effective viscosity and normalize it by the circulation of the quantized vortices for various conditions of temperature, initially there is a certain dependence on the temperature, but after a certain temperature of 1K, it is in fact constant, and a certain number, which is about 1/10 of the circulation around the quantized vortices. I think this is a very simple kind of turbulence where the effective viscosity becomes independent of a number of other parameters in the problem. And this allows me now to sort of summarize what the relation between classical and superfluid turbulence are. And the similarities are that, I didn't show this to you, the classical and the superfluid turbulence both have -5/3 slope in the spectral form. And the decay law is the same as in classical turbulence, this is that. And here is a list of things of superfluid turbulence and classical turbulence. The velocity period follows a power law here, which is -e, in fact, towards the tail. And here it is nearly normal. And reconnections certainly play a crucial role because the power law is associated with reconnections. Here it is not completely clear to me. And quantization of circulation imposes severe restrictions on the stretching of vortex lines, because if you stretch a classical vortex line, for instance, you know that it will spin faster and faster the more you stretch, whereas you cannot do that here. Quantization imposes severe restrictions on what you can do. And vortex stretching, we know, plays a very important role in energy transfer. Dissipation mechanism is not well understood. Here, one thinks it is due to fluid viscosity where dissipation occurs. And the effective viscosity is slave to the quantum of circulation here in the superfluid case, and the effective viscosity depends on the flow there. So there are a number of things on these matters of which we know very little, and we are beginning to understand only some of them. Perhaps I'll skip that. So brief chronology of this is, whatever I've said is not exactly all new. 1950s, Holland-Wienen indirectly inferred that there are these quantized vortices. And for quite some time it was dormant until 1980s when Klaus Schwarz at IBM and Joel Koplik in City College started doing vortex dynamics calculations. And they did the calculations at some point, and you remember the movie I showed where the reconnections all that you have these tangles, and that was actually 1980s. And thereafter it sort of disappeared from the scene. And around mid-80s, now where we've been able to visualize things and we've been able to measure things that people didn't know how to measure before. And I think it has now taken a life of its own, and I don't know how long this life will stay on. And so, perhaps I can stop now, or can take another 2 minutes.
2 minutes.
Okay, fine. So, I think the similarity between the two fields, that they decay similarly and they have the same power law in the spectral density, must be because in the inertial range, the properties of turbulence do not depend upon many details. If you have a source of energy at the large scale and a sink of energy at the small scales, somehow the transfer, whatever that is, will allow you to have some kind of simplicity in the inertial range. If this is the right picture, then the precise mechanism for dissipation or taking away energy does not matter. In classical turbulence it is due to viscosity, in quantized turbulence it is due to something else which we can discuss. And you produce energy in the grid turbulence, for instance, in very similar ways. So you have energy production in both cases and energy dissipation in both cases. And somehow, therefore, there is this intermediate range where the properties will be sort of similar. And on the other hand, there is a difference. The difference I showed you in the PDF and many other things which I did not show you. And I want to say a little bit about why the difference might arise. So the diameter of a vortex line here is of the order of a few angstroms. So it is a very tiny object, and there may be a few millimeters in length, for instance. And the average separation distance between them is of this order. In the decay experiment, you can actually compute that, and it's of the order of, let's say, 1/10 of a millimeter to 1,000 of a millimeter. This means that the volume fraction occupied by the vortices in these experiments is of the order of 10 to the power minus 3 and smaller. So even though they may look tangled everywhere, the vortices are so tiny in diameter that the volume they occupy is really very little. This is quite different from what we might see in classical turbulence. And the characteristic length scale for effective viscosity, you remember I showed you a graph of effective viscosity, and that effective viscosity has a length scale and a velocity scale. And the velocity scale, let's say you take from experiment, from the decay, for instance, and the characteristic length scale is the order of 1 centimeter. So the ratio of the vortex diameter to separation distance to distance between reconnections, which is what I sort of assume is what this characteristic length scale for effective viscosity is. So if you interpret it that way, it is of the order 1 to 10 to 100 in rough order. And if you recall from your reading of papers on dilute gases, at least in ordinary temperatures, the atomic diameter, separation distance, the interparticle collision distance is of the same order, 1 to 10 to 100. So I imagine, therefore, you can do some kind of statistical mechanics of these long, tiny objects somehow. I don't know how to do it, and I don't know that anybody knows how to do it. So these vortex lines, which are very thin and normally separated by distance which is of the 10 times the diameter of this, and moving about, but then before they hit another and reconnect and do anything else, it would take about 10 times longer, 10 times larger distance. And therefore it's possible, perhaps, just as you can do kinetic theory here, relatively simply, you can do the kinetic theory here. This, of course, if you do it, then you would have made real advance, but I don't know how to do it at the moment. Thank you.
Thank you, Springer, and we have time for questions. Let's start with Bosley.
First, a comment. My claim is that two critical aspects of turbulence not well understood. One is cascade, another is aerodynamic noise generation. I think vortex reconnection is the essence for both. The question, but then also I have a comment regarding the distribution of the exponent alpha. repulsion, so-called, is connected with the, is dependent on the incidence angle of the reconnecting zone planes. Depending, if they are parallel, they will take much longer, if they are parallel, they will come much closer. So that is why I think the spread in the PDF on alpha.
Yes. May I make a response? It's probably right that reconnections do play an important role, and surely reconnections in superfluid turbulence are supposed to be also a source of acoustics. So when you reconnect, the phonons are created and you somehow can, must be able to measure. Nobody has been able to measure that. What I'm really saying is, I don't know anyone who has really shown the direct connection between sound generation and vortex reconnection.
Yes,
you
we have
might
A3, the
Okay,
turbulence
alright.
reading in Tokyo.
Okay, I will take a look.
Martin, Carlo, and then Martin.
On the exponents changing, I think part of what Carlos said is also correct. I think.
Meaning if your probability density function goes like a power law,
Yes.
you only have a finite and small number of moments.
Yes, probably.
So that's kind of weird.
Of course, I don't know when the minus third power will change over to something else, and
Well, that's
whether
the
it will
potential,
change.
whatever power it is.
Yeah, this is an issue that I don't have an answer for. If minus third power continues all the way, it's clear that it does not have many moments.
Carlo?
I have a couple of curiosities. The first one is related to the acoustic part.
Yeah.
I mean, when the vortex they reconnect, they should radiate phonons or something. So
Yeah.
this should be a reversible process,
Yes.
something
Yeah.
associated
Yeah.
with the entropy. So in which sense you were saying that there is some doubt about the possibility?
Yeah, that's a good point. And the point that Carlo is raising is that if they reconnect and phonons are created, it's clearly irreversible, but why am I claiming there is reversibility? And the explanation could be, unless one does the calculation, one doesn't know, that you have the vortices connect, just as the connect is when the phonons are created, but what we are measuring is not right at the reconnection point because our resolution is not good enough. We only have finite distance after reconnection and before reconnection. So perhaps the mechanism of irreversibility is around the vortex line, but not in the far field. That is, if you go far enough, you have irreversibility in some sense. So you have to have an inner dynamics somehow that is irreversible, matching with the outer dynamics that is reversible, as I am saying. And such calculations have not been made, but they can be made.
And the other thing is, in a sense, somehow related. I mean, when you do in classical fluids vortex methods, I was thinking of the Carlo Bareni simulation
Yeah.
using the vortex method.
Yeah.
Then you have to regularize, because when you have the curvature, then locally the intervals they diverge.
Yeah.
This regularization is done theoretically by matching with the inner core dynamics somehow. So in this case, in which you don't really know what's happening inside the core, how they do regularize this?
Okay, this is by a recipe. A recipe that simply is laid down in Feynman's paper a long time ago. And the recipe simply ignores the real details of reconnection, but simply says when they come and when they reconnect, then certain conservation laws are there, and that is all that tells you. So somehow you say there is a reconnection, and thereafter they must come out in a certain topology, and that's all it says. So it's put in by hand.
And just I mean, a comment. I'm aware that Chorin was doing some statistical mechanics.
Right, yes.
Could that be useful somehow for this one?
Somehow his name has dropped out of this business, and I have to see. I don't really know.
Javier.
I just want to make a comment. There is another case in turbulence in which there is an right place for velocity, and I believe it's -3, which is into the method of turbulence, in which the reconnection, of course, is not important. The reason why you have an precise state is because the dates are due to the fluid very near the course of the vortices, which are important. And when you do the algebra, it turns out that the
don't know this, but yeah.
But this is in 2 dimensions. Right?
Yeah, but the point there is that there you're supposed to more vertices.
The only thing Leonard pointed out to me is something like this. Right. Totally, that's right. So I should really take a closer look at this. I had forgotten that Tony had mentioned this.
We have time possibly for one other question before we move on to stay on schedule. Any other questions or comments? If not, I really would like us all to thank screen. Okay, while Javier is getting his computer connection, I'll mention about his talk, which is, I looked over his shoulder. I think the title is a little different than what we have in the program. But it's I can use that. Effective interdependency on the outer regional boundary layers. It's going to emphasize differences between boundary layers and shell code. And it's by Javier Jimenez, Hoyas, Simmons, and Mizuno.
Okay, I'm going to go back to one delay. I was curious, and when I was doing people in channels, I was curious of why bundle layers and channels are different. And I knew they were different because I had been looking at the experiment. When you look at the experiment, they are different. They look a little different. Not terribly different, but enough to balance the area. So what we did is we did a new code to compute one of the layers and started computing it, and those are the people that did the code. I put this picture of one of the layers because it's done with the pressure and it has a lot of hairpins. Okay, they look like hairpins. You don't see when the pressure, you see something that seems a lot of face.
Some, not a lot.
People like this, so why not? Okay, anyway. So we did this code, and this is our advanced. The simulation that we did is not a huge thing. It goes from a theta of 600 to 2000. And that means that it is equivalent to of my 3 channels, is roughly equivalent to the low Reynolds number. The one of Reynolds number 550 would be around there. Okay. And you see there's a couple of papers. One is having published for a year, and the other. And you see that you have to throw away part of it, but then it begins to do what it should, roughly what it should. And it agrees very well with the experiments. And I stress this a little because now I'm going to start comparing these two channels, and the differences are going to be noticeable but not huge. So you want to be sure that these are not, the differences are not numerical. So this agrees well with the experiment. These are the mean profiles, different, 2 of the Reynolds number. These are the fluctuations, and the experiments are the in red, and this is what they call. The simulation follows the experiment very well, inside and outside, and both places are important because most of the different channels are outside. And now it agrees with the experiment, but it does not agree with the channel. The channel and the boundary layers are different, and they are noticeably different. There are several things in this picture. There are several decisions that you have to take. One of them is to what boundary layer thickness you use. Okay? Because in the channel is clear, the boundary layer, there is a length scale, it is half of the channel. But in the boundary layer it is unclear. So Sergio Hoyas and myself, we went through all the experiments and tried to match as many things as possible. And then decided that the best fit was to use delta 99, which experimentally has been used for a long time. For a known reason, seems to collapse better the channels with boundary layers where they collapse and where they cannot, it cannot. And I have plotted here These are model experiments. We see here are model experiments. So the symbols are experiments. Everything in colors, in channels, everything in black and white are boundary layers. Okay. And then this is a log. This is a log scale, and it's done on purpose because that means that if you change the length scale for the boundary layer, you don't stretch these things. You just move them to one side or to the other. Okay. And then you see that the channel, the molecular channels, which are these color lines here, and the boundary layers, which are these color lines there, they're never going to match, even if you apply them to one place. They're just different. Okay? And the same with the same is true with experiments. And it's one of these things that is not, doesn't seem to be a low Reynolds number effect because it gets worse with the Reynolds number. So the channels are here, and the boundary layers are high Reynolds number.
The delta plus values say for channel boundary layer.
The delta plus, yeah. Well, no, I mean, here there is a bunch of Reynolds number. These are low, these are high Reynolds number, these are lower, but these black lines, especially this black line there, should be equivalent to that blue line there. Those are matched. So this is where I'm going to, from now on, I'm going to be using basically these 2 points because this is where the boundary layer and the channel are the same. So you see that the same thing is true for the span-wave velocity. The span-wave velocity of the channels is also lower than the span-wave velocity of the boundary layer. By less than here, this is egregious and this is not dramatic. The thin-wave velocity is also different. I thought that it was not different, but when you look at a thing with a uniform pole and things like that, they are that's different, but not as bad as this. The pressure, we say later, is very bigger. So now why? Okay, this is a long story. I can't give it here, but I'll tell you the version. Because then I want to move to something else. I don't know why I have a small peak on my slides there. Here. Okay. Okay. So the reason why you have, I mean, what you really have is more transverse velocity component and more pressure. Okay. And the reason that you have that is because your energy production is higher in the boundary layer. You can see that here these 2 delta pluses are the same, and this is the production batches, for you, which is the production batches for the energy. And then you see that the production of you in the boundary layer is higher than the production for the channel. I have to warn you that this production, this is Y, this production has been multiplied by Y, so that you can see what happens outside. Because otherwise, it involves by 1 by Y, and you don't have to match yourself. But still, what happens outside is important because even if it goes like 1 over Y is something that is not integral when you go to infinity. So a lot of the energy is okay. And now the production is higher, and this extra energy that goes into you gets into the pressure strain curve. And so the pressure strain which is here, the pressure term is the one that redistributes the energy has to go somewhere, and before it goes somewhere, it has to isotropize to get into some kind of cascade. And this is done by the pressure, of course, it's only done by the pressure. And then you see the pressure strain is also stronger in the boundary layer than in the other. So the question now is where is this extra energy coming from? And then where it is coming from is obvious. You can, the production is the product of the Reynolds stress times the U1. And then you compare the Reynolds stress in the channel in the boundary layer. And they are different, but not so different. What is really different is the U1. The U1 is stronger in boundary layer than in the channel, and we know why, because this is what is called the weight component for the mean velocity profile. If you remember how the profile for the mean velocity bump in the boundary layer where they had the bump at the top, which is not in channel. Okay? The channel is much weaker. And this means that there is an extra UY there, and because there is an extra strain, an extra shear, that means that there is more energy going into the flow. This is the energy that then goes to feed this extra feed. And well, now the question is why is there a path? Okay, why is there a weight? And that is, I mean, people have been saying that for a long time, but now we can check it. It is there because of intermittent. It is there because you have this entrainment of irrotational fluid into the edge of the layer that is not there in channels. In channels, everything is turbulent. And yesterday we saw one simulation in which the outside was turbulent, and then the weight went away. Okay, this is due to the intermittency here. And you can measure intermittency in DNA very nicely because this basically is a question of making the difference between rotational flow and rotational flow, and the vorticity that you can measure. So these are the PDF, or the core of the PDF of the vorticity magnitude as you move away from the wall, and you move away from the wall. There are much longer cases here. I cannot show you the sentence. And you see that what happens as you move away from the wall is there is this delta function appearing as zero, and that is zero rotational. Okay? So essentially, you want to differentiate between flow coming from outside and flow coming from inside. We have condition things of whether you are in this delta or you are not in this delta. So when you are in this delta, you can, for instance, measure the streamwise velocity when you are in the delta. This is the potential part here, and you measure it in the rotational part there, and then you see that the potential part is fast. Okay? There are no Reynolds stresses in the rotational part. There is nobody to break that, and then that flow that is coming fast from the top just out into the layer and goes faster. And this is what appears as an extra velocity, as an extra mean velocity in the profile, and then it appears in the weight and the product. Now, somehow, I mean, this flow is fast, but somehow it has to accommodate with the rest of the layer. And there is nothing to do with but pressure. Okay? When you have potential flow, the only thing that can move potential flow is pressure. So the pressure has to be doing something out there. The pressure has to be different. It's something like almost a prediction. So the pressure has to be different in boundary layers in the channel. And it is very clear. These are profiles, and these unfortunately are all coming from DNA. And these Raymond numbers are no profile. We don't know the last. We learned yesterday. Now there are a few from experiment, but when I plotted this, there were no pressure profiles for this Raymond number. So these are the channels in color, and these are the boundary layers, and my boundary layers. They are your boundary layer, the shadow boundary layer, and there is another one. There is somebody else. Yes, there is a height, blue height, and then you see that all the internal flows are higher, and all the So these are boundary layers. So the particular, sorry. And these are channels. Okay, all the internal flows are down here, and all the layers are there. And then you see that the difference is actually in the weight part. Once you get into the inner part of the layer, the slope of this and the slope of that is different than you are coming from out. Stronger fluctuations which are happening also. And you can also see that if you condition the flow into potential part and into turbulent part, the flow in the pressure into potential part is much higher. This is the mean pressure that is going down because of the square, okay? And this is the mean pressure of the channel that you see is also going down but less because the square is stronger in the layer. And the reason between this and that is that the turbulent boundary layer is out here, and the part is out there. So you can trace it. You can trace. I mean, when you have this system that you have in your computer, you can look at everything. I mean, one of the beauties of the pleasures of DNA, and you can see where is this extra negative pressure in the boundary layer, and it's coming from the vortex, coming from the bottom of the vortex, where we want to have nerve depression. And you can see here by looking, for example, at the PDF of the pressure. These are the PDFs as a maximum of 1 for the pressure in the potential part, and those are symmetric. And when you look in the turbulent part, you have a negative state, which is where the forward box and when you look at the channel, the boundary layer and the channel, the PDF is the positive part, which is the part that to the strain, is the same in both cases. Where you have the stress or the okay, so I mean, before I finish, I want to spend my last 5 minutes speaking about some minor detail that I discovered doing this, which is something that I have been told a long time and I have believed, but it turns out not to be true. I mean, we all know, or I knew, okay, because I have been told by everybody, that the largest structures in North Africa are narrower than
Narrower than the span-wise there.
yeah, narrower. The boundary layers are 1 and the standards are 2. Okay? And when you do the one-dimensional spectra, here is a one-dimensional spectra, a function of the span at much reference number. That is clear. Okay? The boundary layer is this thing that is black, and the channel is this thing that is red, and there is a factor of 2 in the width of 1. It's not. When you do the two-dimensional spectrum of that, it is that. The spectra are exactly the same. The boundary layer and the channel are exactly in the same place. The difference is that the channels are longer. And because the spectra is tilted this way, because you create these velocity things located here at this distance, which is roughly 2, 3 delta or something like that. And then they become longer and they meander and they join with each other and do a thing. So when they become longer, they become wider. If they become much longer as in channels, then when you do the one-dimensional spectrum, you integrate here. And you see this wider part. This wider part is just coming from the thing. And it's not even clear that the boundary layer is really short, because these are long distances. This is basically 20 delta. And by 20 delta, the boundary layer is not a parallel flow. So you are not taking the spectrum at the same height. So you might be here, you might be comparing here what values are not the same. I mean, they're actually not. If this spectrum, I think, is at 0.3 and 0.5, I think it's 0.5. Yeah, 0.5. Yeah. Okay. And here, this is 0.5 here, for the boundary layer there is 0.5. So it is, I mean, essentially, even in this, I mean, boundary layers and channels are a weight of intensity. So I want to remind you of something, because it reminded me of something like this. There is another famous place in turbulence in which there is something narrower than the other. In the buffer, the buffer layer, B is narrower than U. The streaks are 100, B is like 60. Okay? And that has always been a problem. Many curious things written about that, some by me, and they have never been convinced even by me. Okay? Why the wavelength of B, the span-wise wavelength of B, is lower than the span-wise wavelength of B. And the reason is because it is not. Okay? When you look at the spectrums of B and the spectrum for U, B and U are created at the same place. But then U, the streak, keep getting longer and wider and meandering and do all the things. And yeah, and that is my last. And B does not. I mean, B hardly not very dies immediately. So this is something that will maybe Carlo will like that, because anybody that has done any linear analysis of the mean velocity profile of turbulence near the world knows that the most simplified thing is not 100%. And we're always hiding there, like 100 is 160. The gradient of the street is 160. So this is if I clear somebody there. do is I compute the correlation, of course. Okay. Then when you compute you can always SST, and you can always fully perform the correlation together effectively. But then of course it's not real because the correlation is not symmetric. And then you say, okay, I have to window it, I can only graph this up to this distance, okay, and my window it become up to the distance in which the imaginary part of the spectrum that I will get if I do window is less than 5% of the real part. Then what I'm showing you there is the real part, but the window part of the spectrum.
Okay, but you know, when we do experiments in the span-wise, we systematically move the two probes and look at the two-point correlation, and those differences in widths are determined from that.
Oh, span-wise is no problem.
Yeah, no, but okay, but then I suppose so. You're saying they're different. Those widths are different because the aliasing across the other side.
Well, it comes from a string-wise wavelength or temporal wavelength, which are very long, which are in the channel but not in the boundary layer. I mean, span-wise, my spectra are like yours.
Yeah.
And they are but when you look at where this energy, this wide energy here is coming from there. Because here
no, I understand, but still you're still going up between boundary layer thicknesses and I mean I think you have the same it's even more complicated. I mean if you could do a time series spectrum and show it then you
I don't have the data.
Doesn't have enough samples
yeah.
in the time series.
I can't do that, but I mean, basically, you are not going to do anything different from that.
Well, I mean,
this part is okay, because here, the correlation function is metric. And the point is that this part is the same. And I'm telling you that this difference might be something else, even because when I compute it, it's not a problem of whether I'm computing well the spectra far away, that all the spectra do not exist. I'm looking at places in the weather which are different. I'm not sure what to say, but I'm sure.
Falsely, and then
what I was quite struck, that even in the near region, whatever we saw, there are notable differences, like the E prime peak for the channel and boundary, as well as the tau, are different. And that's quite surprising to me.
No, P prime is actually, I don't have that plot here, but when you plot P prime at the wall for boundary layers and for channels, I mean, boundary layers are higher, and that's happens
in the peak Y profile you showed. Now, I have a question. It seems to me that V should be quite different, the Z spacing, because associated with each streak there are two vortices, whether you believe in hairpin or not, even if they're staggered as I claim, in shuffle work. So the V spacing will be almost half of it. Yes.
No. You're saying 60 is about half of 100?
Yeah.
That's what he said.
And you can draw. You draw the streak.
Plus, minus, plus, minus.
Yes. So associated with the vortices, wait a minute. Associated with the vortices, the V spacing is double. The one side is down, one side up. Is it true?
Okay, this will take some private discussion. Philippe's last question, so we can stay on time.
I just have a very brief comment which connects to what Ivan was saying. I mean, I was looking at some time series in the simulation and having span-wise resolution, so I could actually do, as we discussed before, the frequency and span-wise wavelength two-dimensional spectrum. And there, actually, I see the peak at, let's say, the narrower span-wise size, similarly as in the 1D spectrum. But I guess this is, we can afterwards compare the various spectrum.
Okay, well, we're changing computer. And a quick comment, Srini.
I have here the production
production is different in the two cases you said. Usually you would think that the production goes much more into U, and then it gets sort of spread into V and W. So why is it that the U components are very close to each other and only V and W are different?
I don't know. What I think is because the use, because the extra velocity goes into U, but it goes into a term that is 2 U prime. Okay? While the other it goes completely into V prime square. I mean, you have a more difference of U because most of the energy goes into the short term with the membrane.
Let's start with the starting.
Thank you, Javier. Last talk before coffee is by Hiroyuki Abe from Japan, JAXA, and Bob Antonia and Kawamura. And the topic is correlation between small-scale velocity and scalar fields in thermal travel.
Thank you for the class. I'd like to talk about this topic. And this is other on this topic. In this talk, I'd like to talk about the similarity between these two vector fields, such as the fluctuating velocity and also the fluctuating scalar derivative. Also the similarity between the velocity and scalar field and the roll pressure will be mentioned briefly. Ability to meet scale contains one of the major characteristics of turbulence. Here the large scales play a major part in transporting the scalar, while the small scales are important for implementing the mixing at the molecular level. Here when we consider what it is important to study how the small scale mixing is affected by the flow field. One possible answer is that in all turbulence, the small scales are not only stretched by the mean shear, but also distorted by the organized motion. This situation is encountered in reactor flow with a wall such as the combustion chamber. In this context, DNS can provide reliable information at any time and location, and maybe one useful tool to examine these small scales. For carbon channel flow, the first DNS of the with passive scale transport was performed by Kim and Moi for the friction Reynolds number 180 with the internal source heating. Here they use the three quantum numbers, 0.1, 0.7, and 2. Later, effects of the Reynolds and quantum numbers, also the thermal boundary conditions investigated intensively. In the previous study, the focus was mainly on the large scales. As for the small scales, Anthony and Kim examined the isotropy for these two friction Reynolds numbers and quantum number 0.7. However, there was no attempt to investigate the special structures associated with these small scales, especially near the wall. In the present study, we used our DNS databases for the three friction Reynolds numbers, 180, 395, and 640. The molecular quantum number is set to be 0.71. The main objective is to study the structure of the velocity and scalar dissipation field. In particular, we try to quantify the correlation between these three fields. Here we take the following approach. The focus is on the relationship between the three components of the fluctuating velocity vector and those of the fluctuating scalar vector. In particular, we compare mean scale values, transport equations, correlation coefficient, and instantaneous field associated with these two vector fields. Also, some attention is given to these two quantities, such as entropy and scalar entropy, since these variables have a significant attention in isotropic turbulence. And this is a Newton methodology. In the present study, we use the finance difference method in the steering at forward direction for the the one direction, second order center difference is used. Another equation is somewhat as follows. In the present study, we use the constant heat for external boundary condition proposed by Pisaghi et al. Is used. This is the finite energy equation. This is the source term. This is not constant, but the time dependent. However, the statistics obtained from this simulation is very similar to those obtained from the internal source heating by Kim and Moine. And this is the competition parameters. In the present study, we have used relatively large amount of grid points to resolve the small cells. As for the spatial resolution, in the story mass one direction, about the spacing is about 3 to 4 in wall in, while the one direction about the maximum 8 in wall in. Also at the center line, the spatial resolution normalized by the Cronenberg scales is about 0.8 in the story mass and sperma direction, while in the one direction about 1.6. Also, for small scale research, the Taylor Reynolds number is one important quantity. In the present study, the most of the values are less than 100. You're showing the result. I will show one result on the taking the numerical method, numerical accuracy. This is the experience spectra at the center line. This is the velocity fluctuation. This is the temperature fluctuation. Wave number. This is streamer wave number. Normal by either Cronenberg scale and Bachelor scale. And the spectra is multiplied by K4 to see the high wave number behavior as accurately as possible. The present results present results do not show any power up at the high wave numbers, and agree with the result model as well. Now showing the result. First, this is the mean scale values normalized by all units. This is the positive component. This is the scale derivative component. As you see, there is a similarity in form between omega 3 and the theta 2. And also there is a similarity between omega 2 and theta 3. On the other hand, there is a difference between omega 1 and the theta 1. This latter difference is because the omega positive is the solenoidal and the scale derivative is the laminar is measured. Also, this is the same mean scale values, but the different normalization, such as Cronenberg and Bachelor scales. When the isotropy is satisfied, this positive component goes to one third, while the scale derivative component is one over third. As you see, the either the vorticity and the scale derivative component does not go to the isotropic value to the term. Also, there is a larger isotropy for the scale derivative components and for the velocity component. This is consistent with the previous experimental result by Srinivasa et al. And also the Krishnamurthy and Antonio. Now, I'd like to focus on the similarity between the velocity and scale derivative. In this context, first notice the first indicates the similarity when comparing the transport equations of entropy and scalar entropy, while although the velocity is the solenoidal, temperature derivative is the laminar in nature. This slide shows the same transport equations of the scalar entropy and entropy normalized wall units in the present flow. Each transport equation consists of the 7 terms, such as production terms and turbulent diffusion, molecular diffusion, and the dissipational term. As you see, there is a similarity in form between these two transport equations. This is a budget context of these variables, as you see, except very close to the wall, there is a similarity between these two bodies. This is not a difference due to the different neurolinking behavior between these two quantities. Also, near the wall, the magnitude of the mean production associated with the mean velocity and mean temperature is almost the same magnitude as the thermal production term. On the other hand, away from the wall, the thermal production balanced by the displaceable term as in the isotropic term. So wonder how these two vector correlated across the channel. This slide shows the correlation coefficient between these two vectors. Eventually, there are four model correlations. First one is the omega 1 and theta 3, this one. Second one is the omega 2 and theta 3. The third one is the omega 3 and theta 1. And last one is the omega 3 and theta 2. These magnitudes are large near the wall, but they decreases toward the channel center line, this way. In particular, near the wall, these two variables, two correlation coefficients such as the omega 2 and theta 3, this one, and the omega 3 and theta 2, this one, are almost the same magnitude as the correlation coefficient of the U theta, almost perfectly goes to 1. So this is reflected in the instantaneous field. This is the instantaneous field training plan. As you see, there is a good similarity between the omega 2 and theta 3. And also, there is a similarity as theta 2 and omega 3. This is mainly due to the extent similarity between the velocity and the scalar stories. Also, that is the omega 2 and theta 3 appears at the interfaces between the stories, where the theta 2 and omega 3 appears at the edge of the stories this way. So we wonder which one is the best similarity. This slide summarizes the neural correlation coefficient among the 5 variables. Eventually, this correlation coefficient, omega 2 and theta 3, is with the largest correlation among these variables. This is due to the reduced effect of the pressure gradient. In this context, the governing equation of the stream velocity fluctuation and theta can be written in this way. Here, the difference is this term, such as the fluctuating pressure, stream pressure gradient. So at the wall, we have this relation for the second derivatives. So this is associated with the pressure gradient term. Here we look at the Taylor series expansion of these two quantities near the wall. There is also the difference between these two quantities, such as this second term. This second term is associated with the pressure gradient term. Also, looking at the new instantaneous field at the wall, we see the difference between the two quantities. This is the U, this is the theta, almost at the wall. As you see, there is a difference between these two quantities where the large magnitude of the dP or dx, such as the stream pressure gradient, appear. This region is closely associated with the broadcast pressure evaporation. So in the context of the similarity between U and theta, the effect of the pressure gradient cannot be evaluated. So similarly, if we consider the Taylor series expansion of the U3 is the span-wise velocity fluctuation, we also obtain this term. This is also associated with this pressure gradient term. However, if we consider omega 2, in this case, this term this omega 2 is not affected by the pressure gradient term. Hence, the similarity between omega 2 and theta 3 is very almost excellent, almost perfect as a whole. This is why this correlation coefficient shows the largest magnitude near the wall. I'll show 3 more slides. This slide shows the instantaneous field crossing prime. The focus is on the outer region. As you see, the similarity between U and theta in the outer region is not as good as in the near region. So that the similarity between the enthalpy and the scalar enthalpy in the outer region is not as good as in the near region. So as for this scalar enthalpy, we see that here scalar enthalpy exhibits a C-track structure. This is almost similar to the isotopic curves. This shows the relationship between the vorticity and these 3 quantities. Here the vorticity is here the Q, positive Q is used as a vorticity indicator. As you see in the outer region, there is almost perfect correspondence with positive Q and enthalpy, and while the energy dissipation appear around the vertical structure, right in the isotopic structure. Also as for the scalar enthalpy, this scalar structure appear around the vertical structures. This is instantaneous view, but the streamer, the Warner prime. Again, there is the again similarity between the U and the theta in the outer region is not as good as in the near region. That is the inclination angle of the large scale theta structure is much larger than that of the large scale U structure. Hence, the similarity between this enthalpy and the scalar enthalpy in the outer region is not good as that in the near region. So now conclusions. In the present study, we have examined the relationship between the 2 vector fluids across the tunnel. We obtained 5 conclusions. First, near the wall, the scalar derivative vector is closely associated with the positive vector, reflecting a near organization. Second one is that the maximum correlation is with session coefficient is obtained within these 2 variables. This is reflected in the relative role of the pressure on this normal positive fluctuation. However, from the wall, however, this situation is changed, and the scalar derivative vector is less well correlated with the positive vector. Also, in the outer region, there is a concentrated scalar enthalpy, which is almost similar to the isotopic term, such as structure. Finally, correlations between the 2 small scales in the outer regions are almost comparable to those for the isotopic balance, but those near the wall exhibit major differences. Thank you for your attention.
We have time for a few questions or comments. Srini?
Since these comparisons are limited in some sense, that is, they're limited either near the wall or away from the wall, and one component with the other component, do you have an idea as to how this might change with Prandtl number? Do you know? Do you have some sense of how the comparisons you made could depend on the Prandtl number?
Of course, yes. In this case, yes. We use the Prandtl number points as well.
Yeah, I understand.
Yes.
There is no study made of these things for another Prandtl number
No,
9.71.
I think we choose a very low Prandtl number. In that case, we always see the large scale
I want to just the comments also we have discussed this. It's sort of, I think it would be maybe more interesting to use function number 1, because why do you use 0.7? That's because that's there. Function number 1 is sort of, then we can take away the difference in and then we could do 2.5, 1.5, 10 and see what is the qualitative effect. But there is nothing special with 0.71.
But if I understood it correctly, he says that these results are unique.
Yes. But
Unique. But he does not expect them to happen.
Are they unique? Presumably, it means it is good for a unique.
Yeah. There's small differences.
Do we understand correctly?
Yes, I understand, but I think the existing experiment is just mostly quantum number 0.61, right? So,
But are there any experiments that you can compare?
right.
So that's a nice thing with BS. You can do whatever you like. You can choose.
Was there a hand in the back I missed from the last time? Positive.
you seem to make a somewhat tangential point, seems to be reasonable, but I'm not sure you explained it, that near the wall the pressure is connected with omega 1 but not with omega 2. Do you have any explanation? No, in the conclusion you have
This is yes.
the connection between
Between
omega 1 and
this
omega
means that connection between the omega 1 pretty much pressure gradient, right? As you said. This is closely associated with the particle structure in the buffer region.
See, the pressure fluctuation is associated with the vortical structure.
Yes.
So the streamwise vorticity is associated with nearly streamwise vortices.
Yes. Yes.
So the correspondence is clear, but omega 2, which is wall normal, is not vortex, it's a sheet across the flank of the street, and therefore there is no compact vortex, and therefore you would not have the connection between the two.
Okay, I think we should stop for coffee. Let's first thank the Next session will start 5 minutes after that.